Welcome to the session on working with geometries in 3DEC. This is Jim Hazard, 3DEC Product Manager at ITASCA. Okay, by geometries, what I mean is a triangulated surface. And so this is usually a DXF. This is an AutoCAD format. It could be an STL, which stands for, I think, stereolithography or something, which is just a bunch of triangles. And so essentially a geometric surface is a bunch of triangles that define a surface. And again, we can import them. We can import multiple sets. So you could have different geometries for topography or geology layers or whatever you want. Each one of those imported geometries becomes a geometric set. And a geometric set is a set of nodes, edges, and polygons linked together with some sort of name. So importing is probably the most common way to do this. You can actually create geometries from within 3DEC. There are commands for creating shapes, and you can do it polygon by polygon. You could also do it with fish. You have a geometric surface. The whole point is that you can use this to interact with the model. Very commonly used as a filter with the range logic. So you want to find all of the blocks that are above or below some surface. Visualization aid with plotting. So you could maybe just plot the blocks that are above a surface or touching a surface or something like that. You can use the geometries to some extent with model building, and I'll show an example of that. And because the geometries are just another object within 3DEC, you can assign group names to them, you can assign extra variables to them, and when you plot the geometries, you can even contour colors across the geometry surface and things like that. Okay, so things you can do with geometries. Import an AutoCAD DXF or an STL file. These are the formats that are currently supported. You can use this to create blocks. So if you have a nice closed surface, you can actually fill it with blocks or even zoned blocks, which is something you would do in, say, Griddle. You can cut blocks with geometry. So if you import some surface, you could use that to cut through the blocks. You can extrude blocks, for example, upward to match a topography. You can densify blocks close to geometries. That's what's being shown in the picture here. So imagine you import some sort of topography, and there's a command that allows you to densify the blocks so that you have more detail around the topography and less detail further away from that. And I'll show that in an example in a minute. You can import a geometry and use it to define the water table, and this is very common. Painting geometries, this is what I was saying. You could actually contour information on the geometry, and what you can do is you can extract information from the model and then paint that on top of the geometry. And I'll show an example of that too. And as with everything in 3DEC, you can manipulate the geometries directly with fish. So I'm going to show a few simple examples about how you can use geometries. And then we've got a slightly more complicated example, which is a simulation of an open pit. Okay, so if I start 3DEC, I'm going to open up a project, and this will be in the training material that you hopefully downloaded. So in my case, I put it in training, software training 3DEC, and there's a directory called geometries. And there's two subdirectories here. One of them is called geometry. Let's open that one first. And there's a project in there called geometry. So inside this project are a bunch of different data files that show you different things you can do with geometry. So we can just walk through these one by one. Geometry 1 just shows you how to create a geometry with commands. So again, mostly you would probably be importing them, but if you really wanted to, you can create things with commands. So here's an example. So you give a name for some sort of set that you're about to create. So let's, for example, call it tunnel. I can create nodes, I can create edges, I can create polygons. So see how there's a hierarchy here. There's nodes that have positions, there's edges that connect the nodes, and polygons that connect the edges. You can create polygons directly by just giving positions, and it will create a polygon for you. I'm just showing this here so you can see the hierarchy. So if I run this, what we should see in the end is, of course, one triangular polygon with 3 edges and 3 nodes. If I look at the plot on my geometry, there it is. I hit Control R to zoom in. So there's a triangle I just created. By default, it does not show you the nodes, but you can turn them on if you want to. I can go over here under the attributes. And when it says nodes, I can just change to on. And it plots little spheres at the nodes. I can make them bigger. So sometimes this is useful, but most of the time you don't want to see the nodes. Once I've got a geometry, I can manipulate it with fish. Actually, what I'm doing here is creating the exact same geometry I just did, only doing it with fish. So there are commands here, geom set create to create the initial set. I'm specifying 3 points as vectors, and then I'm in this case, I'm just directly creating the polygon by adding nodes to it. So instead of creating the nodes first, then the edges, then the polygon, I just say I need a polygon. Actually, I've created an empty polygon first, and then I just add nodes to it. And the last one here is I close it. And what you end up with is the same triangle that we just saw with the commands. There it is. Okay, going down the list here, the next one is called make topo. In this case, we're going to import a topography. We're going to import a geometry as a DXF. Run these first 2 lines and look at it. So you can see down here, it's imported 1,825 nodes and so on. I go back to my plot and hit Control R to zoom the extents, or press this little button up here. So here's a topography that I imported. You can see it's a triangulated surface. Now imagine I wanted to create a model that matched this topography. One way you can do it is like this. So what you do is you create a layer of blocks somewhere below the topography. You extrude it upwards, and it will intelligently do it in such a way that it will try and match that topography. So, so we create one big block, and then we divide it up 20 in the X direction, 20 in the Y direction, and 1 in the Z direction. So if I just run these 2 lines and go back to my plot, you can see what I've done here is I've made a layer of blocks. The more blocks you create in this layer, the higher the resolution will be when you're trying to match this topography. We'll see in this case that it actually works pretty well with 20 by 20. So I've created the bottom block, and now I just need to extrude it. So block generate from topo. I give the name of the geometry set that I imported. By default, when you import a geometry, and the name is something.dxf, the name that is assigned to the geometry object that is created in 3DEC is the same as the name that was imported without the extension. So I imported topo-fix.dxf. The name of the geometry that's created is just called topo-fix. Usually this is fine. You can actually give it a different name when you import it if you want to. So I'm extruding those blocks upwards, and I'm saying, let's make 10 blocks in the vertical direction, and it will do its best to match that topography. So if I just run that command, generated 7,450 new blocks. Let's go look at the plot. Right, so you can see what happened here. It generates 10 blocks upwards, but they're all not necessarily the same thickness because it's trying to match this topography. If I turn off the geometry, you can see a little more clearly what it looks like. You will also see that a lot of the faces on the surface have been triangulated. Sorry, have been split into two triangles to try and better match the topography. This is fine, it still works. So if you want a fairly accurate match to the topography, this is what you can do. Probably more common to do an octree style mesh, which I'll show in the open pit example later. Okay, going down the list here, the next thing is called tunnel.dat. And what we're doing here is using an imported geometry to cut out a shape. So I can create a big brick, like usual. Note here that when I do the cutting with the geometry, I need to specify a domain. And we'll talk about this in the discrete fracture network section. What this essentially is a domain that defines the extents of the possible model that you are creating. The reason that we need to specify the domain when we're cutting with a geometry is that under the hood, it actually turns the geometry into a bunch of triangular fractures and uses the same cutting logic that the DFN uses. So we have to give this domain, and this is X direction extent, Y direction extent, Z direction extent. Here we're reducing the tolerance. Often when you do this cutting with these geometries, it will result in some very small blocks being formed. Maybe you don't want that to happen. Maybe you do want that to happen. Reducing the tolerance a little bit here from the default to make sure that I actually cut all the blocks that I want to cut with this geometry. So I create the brick. I import the tunnel. Let's have a look at it. Let's just create the brick and import the tunnel geometry, I should say. Let's go back to my plot. Let's zoom into the right position. So here's the big block. And here's the geometry that I imported. It's like a horseshoe-shaped tunnel. Let's make it a different color so it's kind of obvious. If I change the polygons to be, all right, the color list is here. If I change the color to be green, now I can see the geometry. I could go here and make my block transparent. Right, so this is a relatively simple case. You could actually cut this tunnel out with commands. There's a block cut tunnel command, but just to demonstrate how you can use the geometries. Note in this case that the surface isn't actually triangles. It's, in this case, four-sided faces. That's fine. It still works. So I import this geometry, and what it does is it will make a cut for every facet of this geometry. So there'll be a cut here, a cut here, a cut here. And you'll end up with a dozen or so cuts to define this tunnel. So be careful when you do this. If I had a much more high resolution tunnel here with much more facets on it, I would end up with much more cuts in my model. And you can end up with some very ugly block geometries. So I encourage you, if you're going to do this kind of thing, to simplify the geometry as much as possible to get the basic shape of what it is you're trying to cut and not necessarily all the detail. So I've created a brick. I've imported a geometry. Now I can just give this command to cut it. Block cut geometry. Again, I give the name of the geometry that I imported, which again is just the name of the file without the extension. Specifying a joint ID number because maybe I want to give some properties to those joints or join them or do something like that. Probably I want to join them. So let's just run this command. My plot, let's put my blocks back on. Make them not transparent. So now you can see what happened. I can hide my geometry. Right? I made a cut for each one of those faces, and I end up with tunnel-shaped block here that's been cut out of my giant block. And now I can do something with it. Probably I want to delete it or delete it gradually or something like that. So after I've cut it out, I need to identify it. I need to find the block that is associated with this tunnel. And you can do that again using the geometry. So let's just have a look at that command. So the last command here is I'm trying to identify the blocks that are cut by that geometry. In this case, it's relatively easy. You could just find out the centroid, and it's only one block. But you can imagine in many cases, it's more complicated than that. And so what you want to do is find all the blocks that are inside of that geometry. And so we use this range geometry space, and I'll show this again in other examples, but this is the first time you've seen it. So I'm going to give the blocks a group name, tunnel. Range geometry space, tunnel, again, using the name of the geometry that I imported. And then I give this command here, or this keyword, count odd. Now, this is a little bit not intuitive. I'm going to go back to PowerPoint here so that I can draw what's happening and what this count odd actually means. So if I put my PowerPoint here, and let's just make a blank screen. Let's go to draw. Okay, so here's our tunnel. Okay, and we've got a bunch of blocks. Imagine we had a bunch of blocks in different positions, okay? Maybe I should have made them a different color, but that's fine. Now you use this range geometry space. Here, let's make the tunnel a different color so it's obvious. And these, imagine these black things are blocks. I want to find all the blocks inside of the tunnel. So I use this range geometry space and I say count odd. What it does is for every block in the model, it casts a ray upwards. Okay, so imagine I'm sitting in the middle of this block and I cast a ray upwards and I check to see if this ray intersects the geometry. In this case, it doesn't. It intersects at 0 times. Same with this one, 0. Think about this one down here. I project a ray upwards. It's going to intersect once, and it's going to intersect twice. So that one, 2 times. This guy that's inside the tunnel, when I project a ray upwards, it intersects it 1 time. Okay? So it turns out that regardless of the shape that you have that defines your geometry, if you are inside of that shape and you project a ray upwards, you will hit the geometry an odd number of times. Right? Imagine you had a more complicated shape like this. Maybe your block is here. I project a ray upwards, I hit it once, twice, 3 times. But if I'm outside, I hit it once, twice, 3 times, 4 times. So if you're inside the geometry, you're hitting the geometry an odd number of times. And if you're outside, you're hitting it an even number of times. So the syntax is kind of weird, but it actually works. And so if you just say count odd, you will identify all of the blocks that are inside of that geometry. There actually is a keyword that's just inside, which is more intuitive, but it only works if you have a completely enclosed volume. So it checks to see if you're completely, inside of something that's completely enclosed. In our case, remember we have this tunnel. Let's have a look at it again. We have this tunnel, it's open at the end. So if I say inside, it doesn't work because it doesn't really know what's going on inside. So I use this other style of command. Block group tunnel, range geometry space tunnel, count odd. So after I run that, look at my plot, put on my blocks. I color them by group. Right, so now the one inside the tunnel is called tunnel, and all the other ones are called none. That's one way you can use the geometry range. You can also find blocks that are within some distance of the geometry. And you can find blocks that are above or below a geometry, and I'll show that later. Okay, next example. In this case, so in the previous case, we used the geometry to cut existing blocks. In this case, we're going to use the geometry to create new blocks. And so what you can do is if you have a nice closed geometry, you can actually just generate blocks inside of it. And this is using the same libraries that Gridle uses to generate blocks or zones. It's not quite as sophisticated. There are things you can do with Gridle that you can't do here, but It gives you the basic functionality. So let's have a look at this one. If I import this geometry, have a look at it. All right, let's turn the geometry on and let's zoom out. All right, so what this geometry is, it's a tunnel, and then because we're going to create blocks and fill up a volume, we need to have an enclosed volume. So for this to work, you need to have a watertight enclosed volume. And so what we've actually got here is an enclosed volume with a tunnel in the middle of it, but there's actually 4 separate sections here. If I make this transparent, it should be obvious. See how you've got these internal surfaces here. So you can imagine you might create something that has joints in it. Maybe you want to create something that already has faults in it. And so you can do that. You can create this geometry in Rhino or some other CAD program. You can have these internal surfaces. In the end, if you have an airtight geometry, I can fill it with blocks or zones, as I'll show in a minute here. And it's smart enough to know that these internal surfaces should be turned into faults, or at least joint planes. So I import it, and then it's just one command: block generate from geometry set. Again, I give the name of the geometry set that I imported. I tell it something about how big I want my blocks to be, minimum edge length, maximum edge length. It's going to fill them up with tets. Again, we're always using tets in tetrahedra in 3DEC. I can say something about the gradation. There are other keywords here. You can be more complicated. But if we just run this, all right, it created 4,788 blocks. So let's go have a look at it. The geometry, change this block back to, let's just start by changing it back to ID. So here's 4,000 some odd blocks. Again, it fills up the shape with tets. Almost certainly you would want to join these, or at least join the ones that are not separated by real faults. It's relatively easy because what it does is it, first of all, it creates all these blocks, which is fine. It gives them group names. Let's change it back to group. Blocks that are separated by these surfaces are given different group names. So you could join group G0 and then join group G1 and join group G2 and join group G3, and you still have these 4, let's pretend they're real faults. They would still exist. You look at the joints that are created. Let's just do that quickly. So there's joints between all of these tetrahedra, and again, you probably want to join most of them. But what it does, if I change this label to be joint set, again, it's smart enough to, all of these joints between the tetrahedra have one number, but the ones that it thinks are true joints have a different number. So if I just hide the red ones here, oh, that appears to have not worked the way I thought it was going to work. Probably if we zone this, then this will appear the way I expected it to appear. Okay, let's just go back to this example here. Now, in this case, we created tetrahedral blocks. Turn off the joint plane set. Turn the blocks back on. Okay, in this case, in the original case, we created tetrahedral blocks, which you would probably want to join together. This is fine because if you have blocks, you can then do further cuts, because often you might import a geometry or create these blocks and then want to cut a joint set on top of that. If you don't want to do any more cutting, you can turn these blocks into zones as you import them. And you can do that just by giving this keyword merge. And what it does is it merges all those tet blocks together and turns them into zones, at least the ones with the same group name. So if we run this whole thing from the start, So now it's created 4 separate blocks and 4,788 zones. So if we go back and look at our plot, let's change this back to ID, right? Now we've only got 4 different blocks. Change the colors here to make it more obvious. So now we've only got 4 blocks and they're already zoned, which is great. And we even have this zone gradation from the middle outwards, which is also great. If we look at the joint planes, now you can see that these joint planes exist between the blocks. And this worked exactly the way we want to. This is a great option, unless you want to do more cutting and you can't cut something that's already zoned. Otherwise, this works great. Okay, that's the end of that example. The next one, this is something that people do if they're simulating masonry structures. People do this quite a lot with 3DEC. This is a slightly different approach here. We're not importing a DXF or an STL. It's a different format called VRML. The extension is often WRL. So you can create actual 3D shapes, 3D blocks in some CAD program, in this case, probably Rhino. As long as they're convex blocks, you can import them and then just automatically turn them into 3D blocks. So this is super interesting. Let's run this. So somebody spent quite a lot of effort creating these blocks in a CAD program, and I'm just importing them and turning them into 3D blocks. So we can see, let's turn on the blocks here. So you can see what we've got here is a whole bunch of blocks that define some sort of masonry structure here, some sort of vault system. That's basically it. So once you've imported them, you do everything else the same way you normally do. You can fix, in this case, we'll run it rigid. So you can just fix the block on the bottom. You can assign a block density. That's all you need if they're rigid. You give contact properties. Remember, this material table gives you the default contact properties. I can turn on gravity, and I could actually solve it. So just to show you that this actually works, run it. We can go back to our plot. We can contour by displacements. So you can see that it's working and this thing is moving due to gravity. Okay, we don't need to run this to the end. We will now move to the last example, Voronoi. What we're doing here is we're instead of importing a geometry, we're just creating one. This is one of the commands that comes with 3DEC. You can create a box or a sphere or a cylinder, I think. Very common to just create a box. So we say model new, we create a box that goes from -1 to -1 in the X direction. I haven't specified the Y and the Z directions. That assumes you mean the same thing. So I can just run those lines. I can again have a look at my geometry. Oh, sometimes if I'm looking at a geometry that plot item has already been created, I need to specify which model sets I'm looking at. I turn on the cube. There it is. What you can do is automatically create Voronoi within that shape. This only works if it's a convex shape. So if you want to create a tunnel or something like that, you would need to fill up a cube with Voronoi and then do some cutting, cut out the tunnel shape. But if you have a convex shape, you can just fill it with Voronoi. And again, you give some minimum edge length and maximum edge length. In this case, we'll specify them all to be the same, 0.25. It created 888 blocks. We can go and look at the plot. Let's turn off my geometry. Let's go to my block and change it back to label. There we go. So now it's obvious what's happening here. We filled up this block with Voronoi, and it works great. Okay, that's all the general geometry things I'm going to talk about. Now we'll just walk through a more realistic example. And again, I'm giving this to you. So we can open an existing project. I go to File, Open, go up 2 levels. Oh, sorry, go up 1 level into Geometries. And there's a file called folder called Octree Pit. So open that. When we do this course live, I have people type it and we follow along. In order to save time, we'll just open the existing solution. So go into Solution and open the project that exists there. So I put all of this into one data file, but there's a whole bunch of plots that have already been set up here. So let's have a look at it. This is a relatively simple open pit excavation. I mean, in real life, you'd have a more complicated topography and you'd have multiple pit shells probably. This is relatively simple and it runs quite quickly and we can just demonstrate a few things. So model new. Here you can specify a random seed. I've talked about this a little bit before. It's completely not necessary in this case. But we use this particular example in some of our testing. And so I want to make sure I get this exact same result every time. And because there's some randomness when it comes to the zoning, if I don't specify a random seed, I might get slightly different answers. In a real consulting job, that probably doesn't matter. But for our testing, I want to get the same answer each time. So I just give this random seed. We'll run this one in large strain. I put it at the top here so I don't forget later. Again, I can specify some tolerance. It's a little bit less than the default. Here's this command block, join by contact on. We've talked about this before. And what this does is it ensures that you're doing contact by contact joining rather than block by block joining. This is useful in this particular example because what we're going to do is create a whole bunch of blocks, join them together, and then kind of fault through them. And we don't want any of those joins to become unjoined. And if you do the block by block joining, that's often what happens. And then you have to deal with the joins that became unjoined because they're not real faults and you have to give them different properties and so on. If you do this contact by contact joining, you don't need to worry about that. The things that were joined stay joined. And when you make a cut, it becomes unjoined. So probably most of the time you do want to use this block join by contact on, unless you're doing a rigid block analysis and it's important to worry about things like moments of inertia and so on. All right, I start by creating one big brick. In this particular example, it's using imperial units. So this is feet. So 10,000 feet to 16,000 feet. Also notice that this is in some sort of mining coordinates. Often they have coordinates that are not centered at 0, 0, 0. Which is fine. So I create one big brick and I densify it a little bit. So 6 in the X direction, 6 in the Y direction, and 3 in the Z direction, and then I'm just joining them because they're not real faults. I import 2 geometries. One defines the open pit and one defines an ore body. So let's just run lines 1 to 16. All right, and let's go have a look. If there's one of the plots here is called geometries. If I just open that, it's already showing a plot of the geometries. Here's the open pit, and here's some ore body. You could, in theory, make a griddle model or even try to make an enclosed volume here that includes this pit to get a very accurate representation of this pit in your model, and similarly the ore body. This can be quite labor intensive, so we're going to take a different approach here, which we like to call the Octree approach, and I'll show you what that means in a minute. Actually, we can put the blocks on here, so let's just put the blocks on here. Okay, so I've created one big block and I divided it 6 by 6 by 3. It's showing, even though I'm plotting by ID, it's showing all the same color because I joined them. Okay, so here is the most interesting part about this example. We're going to densify the blocks. You've seen this before. But we're going to repeat it 4 times. You say block densify. Let's not worry about this gradient limit for a minute. Block densify, repeat 4. We're going to join them. Trick here is to decide which blocks we're densifying. So if we just said block densify, repeat 4, it would take each one of these blocks and divide them up into 8 blocks. And then it would divide them up again, and then it would divide them up again, and divide them up again 4 times. And you would end up with a whole bunch of blocks here. And you would end up with a whole bunch of blocks down here at the bottom or in the corners where you don't care about what's happening. What we really want to do is have more detail around the pit and less detail away from the pit. And so again, we can use this range geometry distance. Remember before we said range geometry distance, we gave this the name of a geometry and we said count odd, and that found all the blocks that were inside of a geometry. In this case, we're saying range geometry distance. We're giving the name of the geometry. We actually have 2. So we can say, give the name pit, say set or, and I could have even more here. I could say set, sandstone layer, set pit 2012 or whatever. You can have as many geometries in this command as you like. In this case, we have 2. So range geometry distance pit, set or. In this case, instead of finding the blocks that are inside of the geometry, we're finding the blocks that are touching the geometry. So you say gap 0. So all of the blocks that are within a distance of 0 meters, or feet in this case, of the geometry will be chosen. Note, however, that if I just say gap 0, it assumes that you mean all blocks where the centroid is within 0 feet of the geometry. That will almost never be the case. Unless the centroid is lying directly on top of the geometry, it will not get picked. So you give this extra word here, extent, which means that any part of the block is touching the geometry within a distance of 0. So essentially touching. If any part of the block is touching the geometry, it will be selected. So what happens here? It does densify only the blocks that are touching the pit or the ore body. And then it repeats it. So it goes through again and finds all of the blocks that are touching the pit and the ore body and densifies them. And then it does it again, and then it does it again. So if we run this, lines 18 and 19, takes a little bit of time. And eventually it says some new blocks were created, because what it actually does is it removes existing blocks and then replaces them with 8 new blocks. If we go back and look at our geometry plot here where we put the blocks on it, now you can see what's happened. So far away from the pit, we have the original big blocks. And next to that, we have 2 smaller blocks. And next to that, each one of those, we have 2 smaller blocks. And next one of those, we have 2 smaller blocks, and so on, because it repeated itself 4 times. So we have fairly small blocks here close to the geometry and big blocks far away from the geometry. The one part I didn't talk about yet is this, one part of the command I didn't talk about yet is this gradient limit. What this does is ensures that you do not have humongous blocks next to very small blocks. So if it cuts a block into 4, or sorry, if it cuts a block into 8, fine. And then if it cuts it into 8 again, you could potentially have a big jump in block size from one to the next. And so what it will do is it will cut the adjacent blocks to make sure you don't have that big jump in size. So if we go back and look at the plot, you can see that even though these guys here are the only ones touching the pit, it makes sure that the change from the small ones to the next ones is only a level of 1. And from those guys to the next one is a jump of 1. And from this guy to this guy is a jump of 1. You don't have a jump of like 16 blocks touching 1 block, just to try to make this more gradual. So probably most of the time you want to use this gradient limit keyword here. Okay, so that's the densifying. And that's what we like to call an octree mesh. Because it's 3DEC, we will now, well, those are joined, right? Everything so far is joined. None of those are real joints. Now we have a real joint. In a real model, a consulting job, you'd probably have many, many joints. In this case, we'll just make one, dipping at 60 degrees and dipping off towards the left. Just run that line. We can have a look at it. So we go back to our plot. Now you can see it's made a cut. You've got a joint that's coming in sort of close to the pit, so we'll see what happens with that. Now we want to zone it, and let's pretend we want smaller zones close to the pit and bigger zones far away from the pit. And again, we can use this range geometry distance. In this case, instead of just finding the blocks that are touching the pit, we can find them that are within some distance away. So let's pretend we have a volume called coarse zone, and this is within a distance of 500 of those geometries, so 500 feet of the geometry. So what we're doing here is we're first grouping the blocks just so we can visualize what we're doing. Then we have another volume we're going to call fine zone within 100 feet of the pit and the ore body. And once we've assigned the groups, we can generate different zone sizes for different parts of the model. We could have done this all in one. We could have said here, for example, block zone generate edge length 50, range, geometry distance, pit, set ore gap, or whatever. Didn't necessarily need to group them first and then generate the zones using those groups, but it is a nice way to visualize what we're actually doing here. So let's just, if we just run lines 26 and 27, go back to our plot. We click on the block plot item, we can change the label to group. So what you can see, what we've done here is we've got a range. Some of these are called fine zone, some of these are called coarse zone, and some of them are nothing. Now that we have these group names, we can use that to assign different zone sizes to different regions, which is what we're doing here. So here we just generate the zones. Again, we can go back and look at our plot and see how you have small zones in the green region, bigger zones in the red region, and bigger zones in the blue region. Okay, now we set the properties. We want to have different properties for the ore zone. Let's pretend it's some soft, squishy material. So far, we've identified blocks using the geometry logic. It is also possible to identify zones with the geometry logic once we've created them. And because the properties are assigned to zones rather than blocks, we can do that and get a little bit more high resolution here. So we can say block zone group or zones, range geometry space, or count odd. So remember before we said if it's count odd, then it is inside of that geometry. In this case, it's a nice closed surface. So I think we can use the keyword inside here instead of count odd, and it's a little more intuitive what's happening. So let's run this. So now we're only checking the ore geometry, and we're only finding the zones that are inside of it. Let's go have a look at our plot here. We can't see them because they're inside, so let's make a cutting plane. So if I reset to the XZ plane, so I can make a cutting plane in the XZ plane itself. So I go to my block group and choose cutting tool. If I go to the cutting tool, you can see that the plotting on this particular plane is a little bit patchy. If I can move backwards and forward through the plane by using these arrows. So if I just move slightly here, I get a better plot. Sometimes the cutting plane lies right on the boundary between blocks and you get those white patches. So I'll just move it slightly to get a nicer plot. Now I'm plotting by block group here, so I'm still seeing coarse zone, fine zone, and none. We can change that to plot by the zone group instead of a block group. So if I go to the label and I choose zone group, now I can see most of this is none, but this little region here inside of the ore zone has been set to be called ore zones. And I can plot the geometry on top of this to make sure it worked. So let's put the geometries on, but let's also put a cutting tool for the geometries. And let's just change the ore geometry to be red. That's more obvious. So see, I've got this red ore zone here, and it's trying to find the zones inside of it. Again, it finds the zones whose centroid is inside of it. So it's not a perfect match, but it's pretty good. I can go to my cutting tool, and I can walk backward and forward through this to have a look at how it works. You can see this particular view here. It looks pretty good. So there you go. That's how you identify the zones that are inside of a geometry. Some of these guys look to be outside of it, but remember this is three-dimensional, so it's possible that part of this zone is actually inside of it in the other dimension. Okay, so I've identified the ore zones, and now it's just a matter of assigning properties. I'm assuming everything is more Coulomb material. I'm giving properties to everything, and then giving different properties to the ore zones. Note that the properties are in pounds per square foot. So the stress properties like bulk modules and shear modules are pounds per square foot. The densities are in, I can't remember, slugs per foot cubed or something like that. If you're used to metric, these numbers look a little unusual, but this is common in parts of the United States for sure. So we give properties. We give properties to the contacts. So this line 41 and 42 is giving properties to the existing contacts. And this line 43 and 44 is giving properties to contacts that have yet to form. But remember, we're running this in large strain. So it's possible that new contacts will form and we need to somehow assign them properties. In this case, they're the same stiffness, but just with no strength. Probably in reality, you would want to give those new properties some friction. So let's just do that. We turn on gravity. Again, it's imperial, so it's feet per second squared. We install the initial stress. We can use this block in situ topography command. So just as a reminder, what this does is for every zone in the model, it looks at the weight of material above that zone and uses that to work out the vertical stress. It's useful in this case because we have some zones with a smaller density than some of the other zones. So it's not going to be a uniform stress everywhere. Some of these zones have less stress because there is a blob of lighter material on top. So this command is useful. Block in situ topography works out the vertical stress. I give the ratio of horizontal to vertical in the x direction and y direction. So that does that. I fix the velocities of the grid points on the edges. I turn on nodal mixed discretization. We've talked about this before. This essentially gives you a more accurate solution for the plasticity of the tetrahedral zones. You should probably use this most of the time. And then we solve it. We get the initial state. So let's just run everything down to here. If you haven't seen this before, you can put in a return keyword. And what that does is if I run this file, it will run everything and stop when it gets to return. So let's just do that. So I went right back to the beginning. It's importing the geometries. It's densifying. Making that up-tree mesh. It's zoning. Still zoning. Okay, now we assign the properties. We're assigning the in situ stress state. Give a model solve command. It should be quite quick. It should be almost balanced. The surface is flat, so there's not a lot of change in the stress required to reach an equilibrium state here. So here we go. It's almost done. We can go back and look at our plot. Oh, it's just saving itself now. I have the automatic compression on. So let's go back and look at our plot while it's saving. If I change it to contour, it defaults to displacement. I'm getting relatively small displacements. It's a couple sections here with a bit more displacement, but it's generally pretty small. So I'm happy with that. Now I need to excavate. So before I can excavate, I need to identify the blocks that are inside of the pit. So remember, I set the group names up here when I was using the zones, coarse zone and fine zone. I don't care about that anymore. I'm done with zoning. So I can change the group name for everything back to default. Now I want to identify the blocks that are in the pit. And we're doing the same thing we did before. With using range geometry space, you give the name of the geometry. You say count. In this case, we're saying count 1. Count odd would work too, but count 1 is fine. We're going to project array. So let's go back to my plot here. Let's make a new slide. Now I've got my pit. Here I've got a block here and a block here. If I project array upwards from here, and it hits the block 1 time, that's fine, but now I'm picking off the blocks below the pit. If I project array upwards from this one, it'll hit it 0 times, and it won't be chosen. So if I say range geometry space count 1, it's going to find all of the blocks that are below the pit, which is not useful. I want to find all of the blocks that are above the pit. So what I can do is just change the direction of the ray being projected. So if I change it to be in the negative z direction, by default it goes up. If I change it to go down, this one will hit the geometry 0 times, this one will hit the geometry 1 time, and I will then find all of the blocks that are above the pit. So that's what I do. Block group pit blocks, range geometry space pit, count 1, but I need to change the direction to be 0, 0, minus 1. I run these 2 lines. I go back to my plot. Let's change the contour back to label. And let's change the label to group. It means, if you just say group, it means the block group. So now everything out here is default, and all of these pink ones are pit blocks. Expected it to work. I can set the displacements to 0 because the displacements that have occurred so far I don't care about. I can also reset the displacements on the contacts. I can take a couple of histories. In this case, I'm taking displacement magnitude histories at 2 different positions. And here's a command that I think might be new. Block relax. So what I could just say here, I could just say block delete, range group pit blocks. It would delete those blocks and solve it. The problem is that I'm excavating a huge volume all at once. And so there's going to be a very large change in force related to that ginormous excavation. And you'll potentially get a big wave passing through the system. And what you'll often see is significant tensile failure at the surface. So imagine you've just lifted off a huge amount of weight all in one shot. You get a big upward movement very quickly, and you can potentially see tensile failure there at the surface. And this is not realistic because we know in real life that these pits are excavated gradually. So you could do that, excavate block by block by block in a realistic way. That's fine. It's just going to take some time and some effort. Instead, you can use this block relax command. And what this essentially does is it excavates the pit gradually. The way it does that is it actually excavates, it actually deletes all the blocks and then works out the reaction forces required so that there is no movement. So it essentially reproduces the weight of those blocks by applying forces to the surface of the pit. And then it gradually reduces those forces. And there are different ways you can do that. You can reduce them in a linear manner. You can reduce them in a nonlinear manner. You can look at the documentation for more details. You give the number of cycles over which you are reducing those forces. So in this case, I say block relax, nonlinear, 2000. So if we just have a look at the help here, you can see what this looks like. So I just pressed F1 and it brings me to the section of the manual related to this command. The function is here, but what you really want to see is this graph. So you give some number of cycles, and it reduces the forces non-linearly over those number of cycles. And the reason you would do this is because we know that a little bit of confinement has a big effect. At the beginning of this unloading, not much is going to happen. You can unload this quite quickly and nothing really happens. It's when you get down to pretty close to zero confinement that we start to see some action. So often this is a more efficient way to do this unloading in a non-linear manner. So I'm going to unload this non-linearly over 2,000 steps. I need to cycle 2,000 for that to work. And then I can just delete that relaxed condition. I don't have to do this. This just keeps on going gradually more asymptotically towards zero. So those forces are basically doing nothing after 2,000 steps. But just to speed up the analysis a little bit, I can turn this off, and those forces go to zero, and then I can just say solve. So let's do that. We can run this segment. Right, so you can see here in the notes, it tells you that it's applying some reaction forces. Total reaction forces are some amount in the x direction, some amount in the y direction, and a big amount in the z direction, negative, right? So it's pushing downwards. And then these forces are gradually reduced as you run these 2,000 cycles. So I should have run this in advance. I'll just pause the recording here while it solves and then rejoin again in a minute.